Implement next permutation, which rearranges numbers into the lexicographically next greater permutation of numbers. If such arrangement is not possible, it must rearrange it as the lowest possible order, or ascending order. We're given an example of an increasing permutation from its lowest value to its highest value. It's definitely hard to derive an algorithm from this example, but there are two key insights. The first one is that the smallest permutation is increasing and the largest is decreasing. This doesn't really help us at this point, so let's look at a larger example to make it easier for us to figure out what's going on. But first, let's take a step back and think about how numbers increase, because it's a similar process. If we increase our count by 1, starting from 298, we get 299, then 300. The 9 in the 299 has nowhere else to go, and we wouldn't just add 10 to the end of 209. So instead, we reset our 9s back to the first version. In this case, it's 0. And we increase 2 to 3. This is where the first key insight should come in. If you think about the last permutation version, 210, it's decreasing and has nowhere else to go, kind of like the suffix 99 in 299. So we reset it back to its starting value, 012, which is increasing. Let's look at a larger example and start deriving the first part of the algorithm. In this case, our suffix is 5410. It's decreasing and has nowhere else to go, so we need to swap the 3 with the next highest value in the suffix, which is 4. Keeping in mind that this doesn't stop the array from decreasing or being its last version. Because our suffix has nowhere else to go, we need to reset our suffix back to the lowest version, which is just increasing, or sorted. But because we know our suffix is the last permutation version and it's decreasing, we can just reverse the suffix to get the first permutation. Kind of like how 210 goes to 012. It's just reverse. Searching for our swappable elements and reversing the suffix is linear, so our time complexity is O of n, and our space complexity is constant because we're not allocating any extra space. The first part of our algorithm is finding the index of the first element that needs to be swapped and its suffix. We can find the first element by starting from the right and move to the left while the array is increasing, or decreasing if you think about it from the left to the right. If our whole array has been searched and you didn't find the element, that means our array is decreasing and it's the last version of the permutation, and we can just return the whole reversed array. If it isn't the last permutation, we need to search for the next swappable element, or the first element that's greater than our prefix element. We do this by searching the suffix from left to right. Once we find the element, we swap it out with the prefix element, then reverse the suffix.